Welcome to the Bedtime Lab, where the world of science and discovery unfolds like a gentle evening breeze. Imagine yourself nestled in a cozy nook, ready to explore a universe of sleepy facts that will soothe your mind and spark your imagination. Let me guide you through an intriguing journey about Ligo, the Laser Interferometer Gravitational Wave Observatory, and the wondrous art of detecting ripples in the fabric of space-time. You might wonder, what exactly is Ligo? Well, Ligo is a remarkable observatory designed to listen to the faint whispers of the cosmos, capturing the echoes of gravitational waves. These waves are ripples that travel through space-time, stemming from some of the most cataclysmic events in the universe, like the collision of black holes or neutron stars. Imagine a pebble dropping into a pond, creating ripples that spread outward. Ligo does something similar, but on a cosmic scale, detecting waves in the very fabric of space itself. Did you know Ligo is so sensitive that it can detect changes in distance smaller than a fraction of the width of a proton? Just think about that for a moment. A proton is one of the tiniest parts of an atom, and Ligo can pick up a change even smaller than that. This marvelous precision allows it to sense gravitational waves from billions of light years away, opening a window into the farthest reaches of the universe. Speaking of precision, Ligo's arms are 4 kilometers long, and they need to remain incredibly still to detect these minuscule ripples. It's so sensitive to vibrations that even the sound of a passing truck or a distant thunderstorm could interfere with its measurements. That's why Ligo's facilities are carefully isolated and equipped with advanced technologies to minimize any disturbances. Here's something fascinating. Ligo's first detection of gravitational waves happened on September 14, 2015. This monumental discovery confirmed a century-old prediction made by Albert Einstein in his theory of general relativity. Imagine the excitement of the scientists who, after decades of preparation and anticipation, finally heard the cosmic symphony that Einstein had once described. You might be curious to know that Ligo operates in 2 locations within the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. These twin observatories work together, comparing data to enhance the accuracy of their detections. It's like having 2 ears listening to the same sound, allowing them to pinpoint the direction and distance of the source. Here's a delightful thought. Ligo has inspired a global network of observatories working together as part of a collaboration called Ligo Virgo Cagra. This international cooperation allows scientists from around the world to share their findings and collectively explore the mysteries of gravitational waves. It's a beautiful reminder of how science brings us together, transcending borders and cultures. And did you know that detecting gravitational waves has opened up a whole new field of astronomy? This cutting-edge field is known as gravitational wave astronomy, and it offers insights into events and objects that are otherwise invisible to traditional telescopes. It's like discovering a new sense, allowing us to hear as well as see the universe. Let me share something interesting. Gravitational waves travel at the speed of light, which means they reach us from distant galaxies in the same way light does. This allows scientists to study events that happened a long time ago, giving us a glimpse into the universe's past. It's like peering through a time machine, witnessing the echoes of cosmic stories from billions of years ago. Speaking of time travel, did you know that Ligo's discoveries are helping us understand the nature of time itself? By studying gravitational waves, scientists gain insights into how time and space are interconnected, offering clues about the fundamental structure of the universe. It's a profound and humbling exploration that challenges our perceptions of reality. Here's a curious fact. Ligo's advanced technology includes laser beams that bounce back and forth between mirrors at the ends of its arms. These lasers help detect the incredibly tiny shifts caused by passing gravitational waves. The mirrors are meticulously coated with layers of materials to make them reflect light with nearly perfect efficiency. This ensures that even the faintest signals are captured and analyzed with precision. And here's something that might surprise you. Ligo's discoveries have sparked a new wave of interest in the study of black holes. Gravitational waves provide direct evidence of black hole mergers, revealing details about their masses, spins, and even the environments in which they exist. It's like having a front row seat to some of the most dramatic and mysterious events in the universe. As you drift into a peaceful slumber, I invite you to imagine the vastness of the cosmos and the delicate dance of gravity that shapes it all. Feel free to share where you're from in the comments below as we continue this journey together, exploring the wonders of science and discovery. Sleep well, dear friend, and let the dreamy melodies of the universe guide you to rest. Let me take you further along our journey into the intriguing world of Ligo. Imagine the challenge of detecting something as elusive as gravitational waves. It requires an extraordinary level of cooperation and precision. Did you know that each of Ligo's laser beams must be perfectly aligned to travel a combined distance of 8,000 kilometers in order to detect a single gravitational wave event? This alignment process is nothing short of a meticulous dance, ensuring that the twin observatories harmonize in their celestial symphony. Here's a thought that might captivate your imagination. The mirrors at the ends of Ligo's arms are suspended by silica fibers thinner than a human hair. These fibers are so fine yet incredibly strong that they help isolate the mirrors from seismic and thermal noise. It's as if Ligo holds its breath, minimizing any tremor that might disturb its quest to hear the universe's whispers. And speaking of whispers, let me tell you about the astonishing sensitivity of Ligo's detectors. They are so finely tuned that they can discern a change in length of just 1/10,000th the diameter of a proton. To put this into perspective, imagine stretching a rubber band all the way from Earth to the nearest star beyond our solar system, Proxima Centauri, and being able to detect a change in length no larger than a human hair. It's a feat of engineering that borders on the miraculous. You might find it fascinating that the data Ligo collects is not just for the observatory's own use. It's shared with scientists around the world, allowing a collective brain of researchers to delve into the mysteries hidden within. This collaborative spirit exemplifies the essence of scientific discovery, where knowledge is expanded through shared insight and collective effort. Here's a delightful tidbit. Gravitational wave signals are translated into sound waves, allowing us to hear the cosmic events they signify. The collision of black holes, for example, produces a chirp-like sound, increasing in frequency and amplitude as the black holes spiral into one another. It's as if the universe has its own music, waiting for curious minds to listen. Another curious element of Ligo is its ability to confirm the actual distance of gravitational wave sources. By measuring the wave strength and frequency, scientists can infer the distance of these cataclysmic events from Earth. This ability to measure cosmic distances with precision has profound implications for our understanding of the universe's expansion and the nature of dark energy. Let me share something else that might surprise you. Ligo's technology has inspired advancements in other fields, including quantum computing and precision measurement technologies. The same techniques used to isolate and detect gravitational waves are being adapted to improve the precision of measurements in various scientific arenas, highlighting the interconnected nature of scientific progress. Did you know that Ligo's discoveries have even influenced the way we think about the formation of stars and galaxies? By studying the gravitational wave signals from black hole and neutron star collisions, astronomers gain new insights into how these celestial bodies formed and evolved over billions of years. It's like uncovering the hidden chapters of a cosmic novel, revealing the rich tapestry of our universe's history. Here's an intriguing aspect of Ligo's operations. The observatories undergo regular upgrades and enhancements to improve their sensitivity and extend their reach into the cosmos. These upgrades are part of a planned series of improvements, ensuring that Ligo remains at the forefront of gravitational wave detection. It's a continuous journey of refinement and discovery, echoing the evolving nature of science itself. And here's a final thought to ponder as you drift into a peaceful slumber. The study of gravitational waves has not only deepened our understanding of the universe, but also enriched our appreciation of the beauty and complexity of nature. It's a gentle reminder of how much there is still to explore and learn, and how each discovery opens the door to new questions and possibilities. As you settle into your dreams, imagine the endless mysteries awaiting us in the vast cosmos, inviting us to listen, learn, and wonder. Can you picture the immense precision and dedication involved in operating Ligo? It's a remarkable scientific feat that requires both patience and ingenuity. For instance, the observatories employ a technique called active noise control to minimize background noise that could interfere with the detection of gravitational waves. This involves a symphony of sensors and actuators working together to cancel out any unwanted disturbances, much like noise-canceling headphones, but on an astronomical scale. Speaking of scales, did you know that the arms of Ligo's interferometers are 4 kilometers long, which is about 2.5 miles? These lengthy arms are essential for amplifying the tiny distortions caused by passing gravitational waves. Every detail is meticulously engineered to allow Ligo to peer into the depths of the cosmos, capturing the faintest echoes of the universe's grandest events. In an interesting twist, Ligo's detectors are also capable of picking up signals from Earth-based activities. They can detect vibrations from passing trucks, distant earthquakes, and even ocean waves crashing against the shore. Such sensitivity demands sophisticated filtering techniques to differentiate between earthly noise and the heavenly whispers of gravitational waves. Can you imagine the challenge of sifting through such cosmic noise to find the jewels hidden within? Let me share a story about Ligo's origins. The concept of detecting gravitational waves was first proposed by Albert Einstein in 1916 as a consequence of his theory of general relativity. However, the technology needed to observe these waves didn't exist until decades later, making Ligo a testament to human perseverance and ingenuity. It's a beautiful illustration of how long-term vision and dedication can eventually lead to groundbreaking discoveries. Here's something that might surprise you. Ligo's twin observatories are located in Livingston, Louisiana, and Hanford, Washington. This geographic separation is crucial because it allows researchers to distinguish local noise from genuine cosmic signals. The two facilities must detect the same event at nearly the same time to confirm a gravitational wave detection, adding an extra layer of verification to ensure accuracy. It's like having two pairs of eyes watching the universe, each one confirming the other's observations. You might find it intriguing that the data from Ligo isn't only used for detecting gravitational waves. In fact, it has become a valuable resource for other scientific fields, such as seismology and geology. The continuous monitoring of ground motion provides insights into the Earth's interior, helping scientists understand seismic activities and potentially predict future earthquakes. This cross-discipline utility highlights the interconnected web of scientific inquiry. And here's a whimsical thought. The gravitational waves that Ligo detects travel at the speed of light, a staggering 300,000 kilometers per second. These waves are ripples in space-time, caused by some of the most energetic processes in the universe, like black hole mergers or neutron star collisions. When you think about it, these signals are like cosmic postcards sent across vast distances to reach us here on Earth. Speaking of neutron stars, did you know that Ligo's first observation of a neutron star merger in 2017 was accompanied by gamma-ray bursts, visible light, and even radio waves? This event marked the dawn of multi-messenger astronomy, where different types of astronomical signals are used to study and understand cosmic phenomena. It's akin to reading the universe in a new language, offering a richer, more complete picture of celestial events. Here's another captivating fact. Gravitational waves stretch and squeeze space-time as they pass through, but the effect is incredibly small. Even though the events causing these waves are massive, the resulting distortions are minuscule by the time they reach Earth, requiring the extraordinary sensitivity of Ligo to detect them. This subtle dance of the cosmos is a reminder of the delicate balance within the universe. Did you ever wonder how Ligo maintains its precision over time? The observatories undergo regular maintenance and calibration to ensure their components function optimally. This meticulous care involves everything from cleaning the mirrors to adjusting the laser systems and seismic isolation platforms. It's a labor of love, ensuring that Ligo can continue its mission of uncovering the universe's hidden symphonies. Here's a curious tidbit. The first direct detection of gravitational waves in 2015 confirmed the existence of stellar mass black holes, which are black holes formed from the remnants of massive stars. Before this discovery, these entities were purely theoretical, existing only in equations and simulations. Ligo's observations brought them into the realm of reality, expanding our understanding of the cosmos. And finally, consider this inspirational thought. Ligo's success has spurred the development of future gravitational wave observatories, like the space-based LISA project. These new observatories aim to detect different types of gravitational waves, exploring phenomena that Ligo can't observe. It's a reminder of the ever-evolving nature of scientific exploration, where each discovery paves the way for the next. As you relax into the gentle embrace of sleep, let your thoughts wander to the marvels of the universe, where each ripple in space-time tells a story waiting to be unveiled. The pursuit of knowledge is an infinite journey, inviting us to dream, to question, and to explore the boundless wonders of the cosmos. Did you know that Ligo's interferometers operate in a vacuum that's 10 trillion times lower in pressure than Earth's atmosphere? This extreme vacuum minimizes air molecules that could otherwise interfere with the laser beams. It's like creating a pristine environment, almost akin to the vacuum of space, allowing the lasers to travel unobstructed over those vast 4 kilometers. Imagine the tranquility required to listen for the faintest cosmic echoes. Speaking of precision, Ligo's laser beams are incredibly stable and have been engineered to maintain a constant power output with the precision of a few parts per million. To put this into perspective, if the beam's power were the length of a football field, the variation would be less than the width of a human hair. Such precision is essential because any fluctuation could obscure the subtle signals from gravitational waves. Here's something fascinating. The mirrors used in Ligo's detectors are polished to a smoothness where the imperfections are no more than a few billionths of a meter. These mirrors are among the most precisely fabricated objects on Earth. They need to be this perfect to accurately reflect the laser beams back and forth, amplifying the signals Ligo is designed to detect. Did you ever wonder how Ligo manages the tiny movements caused by the Earth's natural vibrations? The detectors are equipped with a sophisticated seismic isolation system that can sense and counteract ground motion in real time. This system can reduce vibrations by a factor of 10 billion. Think of it as a high-tech dance, where each movement is anticipated and neutralized to keep Ligo on its toes. Here's an intriguing fact. Ligo's detection range for gravitational waves extends over 1 billion light-years. This means it can observe events from the far reaches of the universe, offering a glimpse into cosmic phenomena that occurred long before life began on Earth. Such vast distances remind us of the immense scale and age of the universe, and how tiny yet significant our observations can be. Speaking of scale, did you know that the energy released by a gravitational wave event can be more than 50 times that of all the stars in the observable universe combined? This energy is emitted in a fraction of a second when massive objects like black holes or neutron stars collide. Ligo captures the whisper of these cataclysms, providing insights into the incredible power and forces at play in the cosmos. Here's something you might find surprising. Ligo doesn't detect the gravitational waves directly. Instead, it records the effects of these waves on its laser beams. As the waves pass through, they create tiny changes in the length of the interferometer's arms. These changes are smaller than a fraction of a proton's diameter, yet Ligo's advanced technology can measure them with unparalleled accuracy. Have you ever thought about how Ligo's discoveries are shared with the world? The data collected is made publicly available, allowing scientists and students worldwide to analyze and contribute to new findings. This collaborative approach accelerates our understanding of gravitational waves and ensures that knowledge is accessible to all, fostering a global community of cosmic explorers. Here's a curious tidbit. The concept of using laser interferometry to detect gravitational waves was first suggested by Russian scientists in the 1960s. It took decades of collaboration, innovation, and international partnerships to develop this idea into the sophisticated Ligo we know today. It's a testament to the power of collective human effort and persistence in unraveling the mysteries of the universe. Imagine the excitement when Ligo's first successful detection of gravitational waves was made on September 14, 2015. This groundbreaking event confirmed Einstein's century-old prediction and opened a new era in astrophysics. The ripples detected were from a pair of merging black holes, each about 30 times the mass of our Sun, creating a landmark moment in scientific history. Speaking of collaboration, did you know that Ligo works closely with a network of other gravitational wave observatories around the globe? These include Virgo in Italy and Kagra in Japan. Together they form an international consortium, enhancing the accuracy and reliability of gravitational wave detections. This global alliance ensures that the symphonies of the cosmos are heard clearly and in harmony, providing a fuller picture of the universe's dynamic nature. Consider the fascinating use of machine learning in Ligo's data analysis. Advanced algorithms sift through vast datasets to identify potential gravitational wave events. This cutting-edge technology accelerates the process of detection, allowing scientists to quickly respond to celestial events and coordinate with other observatories for follow-up observations. It's like having an ever-vigilant cosmic sentinel ready to alert us to the universe's wonders. And here's a whimsical thought to ponder. Gravitational waves carry information about the nature of gravity itself, potentially offering clues to a unified theory that could reconcile quantum mechanics and general relativity. Ligo's findings might one day help illuminate this profound mystery, guiding us toward a deeper understanding of the fundamental forces that shape our universe. As you continue to drift into the gentle embrace of sleep, let these musings on Ligo and the delicate ripples of space-time fill your dreams. The universe is vast and full of secrets, inviting us to explore and discover. Each revelation brings us closer to the heart of the cosmos, where the stories of stars and galaxies unfold in an endless dance of light and shadow. Did you know that Ligo's sensitivity is so exquisite that it can detect changes in distance as small as 1/10,000th the width of a proton? This degree of sensitivity is necessary because gravitational waves are incredibly faint by the time they reach Earth. Imagine the challenge of picking out such tiny signals amidst all the background noise. To achieve this, Ligo's team employs a technique called signal recycling, where they use an additional mirror to enhance the gravitational wave signals before measuring them. It's like giving the faintest whisper a megaphone, ensuring that even the smallest cosmic ripples are heard. Here's something that might capture your imagination. Ligo's twin observatories, located in Washington and Louisiana. This significant distance allows each facility to detect the same gravitational wave event at slightly different times. By comparing the arrival times, scientists can triangulate the source of the waves with greater precision. It's a bit like using both ears to pinpoint the direction of a sound in a noisy room. Speaking of precision, the timing systems at Ligo are synchronized using atomic clocks, which are accurate to within 1 second every 30 million years. These clocks ensure that the timestamps on the detected signals are as precise as possible, allowing scientists to confidently correlate data between observatories. The accuracy of these clocks is crucial for the triangulation process and for ruling out false positives caused by unrelated terrestrial or cosmic activity. Have you ever considered the impact of the Moon on Ligo's operation? The gravitational pull of the Moon causes tides, not just in our oceans, but also in the Earth's crust. These subtle movements are monitored by Ligo's sophisticated systems to ensure they do not interfere with the detection of gravitational waves. It's fascinating to think that even the gentle sway of Earth's surface is accounted for in this grand cosmic dance. Here's a whimsical fact. Ligo has its own quiet time, when certain human activities are minimized to reduce potential interference. For example, during particularly sensitive operation periods, construction work nearby might be paused, and even lawn mowing is rescheduled. This ensures that the detectors can operate in the most serene environment possible, maximizing their ability to catch the softest sighs of the universe. Did you know that gravitational waves travel at the speed of light? When these waves pass through Ligo, they cause infinitesimal expansions and contractions in space-time. This phenomenon was predicted by Albert Einstein in his theory of general relativity, but it wasn't until Ligo's first detection that we had direct evidence. The confirmation of gravitational waves traveling at light speed is a beautiful testament to the elegance and accuracy of Einstein's theory. Now, consider the role of the Livingston and Hanford observatories in distinguishing between true gravitational wave signals and noise from local sources. Local events, like nearby thunderstorms or even large trucks passing by, can cause vibrations that mimic the signals LIGO is designed to detect. By comparing data from both locations, scientists can filter out these false signals, ensuring that what they observe truly hails from the depths of space. Here's a captivating tidbit. Ligo's detectors use vacuum systems to keep the light in their interferometers from being scattered by air molecules. The vacuum tubes housing the laser beams are over 4 kilometers long, and the vacuum inside them is 1 trillion times lower than atmospheric pressure at sea level. This pristine environment allows the laser beams to travel unimpeded, crucial for maintaining the accuracy needed to detect gravitational waves. Imagine this. LIGO has detected collisions between black holes billions of light years away. These cataclysmic events are so powerful that they convert a portion of the mass of the colliding black holes directly into energy, creating gravitational waves that ripple across the universe. What we observe are the echoes of these ancient cosmic events, reaching us across the vastness of space and time. It's like listening to a symphony composed long before any human walked the earth. And speaking of symphonies, LIGO's data can be converted into sound waves, allowing us to hear the cosmic events as chirps and hoops. This audio representation brings the universe's hidden symphony to our ears, transforming abstract data into something we can intuitively grasp. It's a profound reminder of our connection to the cosmos and the music that plays on scales both grand and minute. Here's something delightful. The success of LIGO has inspired a host of other gravitational wave observatories around the world. Each new facility adds to our ability to pinpoint the sources of gravitational waves and understand their origins. As more observatories come online, our picture of the universe grows richer and more detailed, like adding instruments to an orchestra, each contributing to the harmony of cosmic discovery. Finally, ponder this. LIGO's pursuit of gravitational waves has broadened our understanding of the universe. Yet it has also raised new questions. What other phenomena might produce gravitational waves that we have yet to detect? How might these waves inform us about the fabric of the universe itself? Each discovery made by LIGO opens new doors to exploration, inviting us to continue our journey into the unknown, filled with wonder and curiosity. Let me take you on a journey through the intricate dance of LIGO's lasers. You see, the laser light that travels through LIGO's arms isn't just any light, it's infrared, chosen for its ability to travel through the vacuum with minimal scattering. This choice ensures that the light remains coherent over the 4-kilometer distance, maintaining the precision needed to measure the faintest gravitational waves. Can you imagine the level of control required to keep this light in perfect harmony? Did you know that the mirrors used in LIGO's detectors are some of the most precisely crafted objects on Earth? These mirrors are polished to an atomic level, with surface deviations smaller than 1/10,000th of the width of a human hair. This incredible precision is necessary to minimize any distortion of the laser beam, which could obscure the delicate signals of gravitational waves. Here's an intriguing detail. The laser power circulating within the interferometer is dramatically increased using a technique called power recycling. By cleverly reflecting the light back and forth between the mirrors, the power is increased to about 700 kilowatts. This amplification enhances the sensitivity of LIGO's detectors, allowing them to detect the faint whispers of gravitational waves from across the cosmos. Speaking of sensitivity, the vacuum systems within LIGO are maintained at such low pressures that they're considered some of the largest high vacuum systems in the world. The process of creating these vacuums is an engineering marvel in itself, requiring pumps that can remove vast quantities of air while maintaining an environment that's incredibly stable and free from contaminants. Now, Let's explore how LIGO distinguishes between different types of gravitational waves. With its incredible sensitivity, LIGO can detect waves not just from black hole collisions, but also from neutron star mergers. Neutron stars are the remnants of supernova explosions, and when they collide, they produce gravitational waves with distinct signatures. By analyzing these signals, scientists gain insights into the properties of neutron stars, such as their mass and composition. And here's a thought-provoking concept. LIGO's detectors are so sensitive that they can even detect the hum of the universe. This background hum is the collective signal of countless gravitational wave events from the distant past. By studying this hum, scientists hope to uncover hidden aspects of cosmic history, providing a background soundtrack to the evolution of the universe. Imagine this: LIGO's discoveries aren't just limited to gravitational waves. Occasionally, these detections are accompanied by electromagnetic signals, such as gamma-ray bursts. These occurrences allow for multi-messenger astronomy, where different types of data from a single cosmic event are combined to provide a more complete picture of what's happening in the universe. It's like seeing a movie in both black and white and color, revealing new details with each format. Speaking of collaborations, LIGO's network of observatories is part of a global effort working in tandem with facilities like Virgo in Italy and Kagra in Japan. Each observatory contributes its unique strengths, and by sharing data, scientists can more accurately pinpoint the locations of gravitational wave sources. It's a testament to the power of international cooperation in the pursuit of knowledge. Here's a whimsical tidbit for you. LIGO has inspired artists and musicians who translate the scientific data into creative expressions. Some have composed music based on gravitational wave signals, transforming science into art and allowing us to experience the universe in new and unexpected ways. It's a beautiful blending of disciplines, showing how interconnected our understanding of the cosmos can be. Have you ever pondered the future of gravitational wave astronomy? With each detection, LIGO is paving the way for new generations of detectors with even greater sensitivity. These future observatories may be able to detect gravitational waves from the early universe, offering us a glimpse into the conditions shortly after the Big Bang. It's an exciting prospect, hinting at the untapped potential of this field. And here's a delightful notion. Gravitational waves might one day help us understand one of the universe's greatest mysteries, dark matter. While dark matter doesn't emit light, it may interact with gravitational waves in ways we have yet to observe. By studying these potential interactions, scientists hope to unlock secrets about the composition and behavior of dark matter, shining light on a shadowy component of our universe. Let's not forget the role that LIGO played in the Nobel Prize in Physics in 2017. The prize was awarded to Rainer Weiss, Barry Barish, and Kip Thorne, whose leadership and innovation were instrumental in turning the concept of gravitational wave detection into a reality. Their work has opened new windows on our universe, inspiring countless scientists and enthusiasts worldwide. Finally, consider the impact of LIGO on future scientific endeavors. As we continue to explore gravitational waves, we're uncovering new questions and challenges, driving innovation and discovery in fields ranging from quantum mechanics to astrophysics. LIGO is a beacon of curiosity, lighting the path toward a deeper understanding of the universe and our place within it. With each new discovery, we are reminded of the boundless potential of human ingenuity and the endless mysteries that await our exploration. Let me share something intriguing with you. The concept of gravitational waves was first proposed over a century ago in the 1900s by none other than Albert Einstein. Although Einstein's equations predicted their existence, he himself was skeptical about whether they would ever be observed. Yet here we are, thanks to Ligo's remarkable achievements, confirming a prediction that once seemed like an unreachable dream. Speaking of dreams, did you know that Ligo's observatories are so finely tuned that they can measure changes in distance smaller than a proton's width? This level of precision is astonishing when you consider the scale involved. We're talking about detecting ripples in space-time caused by cataclysmic events happening billions of kilometers away. It's like noticing a tiny ripple in a vast ocean from a single drop of rain. Here's a fascinating detail for you. Ligo's interferometers are housed in vacuum chambers stretching 4 kilometers in length. These long arms are crucial for the detector's sensitivity, as any interference from air molecules could obscure the faint signals of gravitational waves. Maintaining such an extensive vacuum environment requires meticulous engineering and constant monitoring, akin to holding your breath across a vast expanse. And here's something that might surprise you. The data collected by Ligo is so voluminous that it requires sophisticated algorithms and supercomputers to process. This data is analyzed to distinguish genuine gravitational wave signals from background noise, like picking out a whisper in a bustling crowd. The sheer computational power involved is a testament to the collaboration between cutting-edge technology and human ingenuity. Have you ever wondered about the role of Ligo's mirrors? They're not just any mirrors. They're suspended by fine glass fibers to isolate them from vibrations and noise. This delicate suspension system helps prevent disturbances from affecting the precise measurements needed to detect gravitational waves. It's a ballet of balance and sensitivity, ensuring the mirrors are as still as the night sky. Speaking of balance, Ligo's detectors must contend with a variety of earthly interferences, from seismic activity to nearby traffic. These vibrations can mimic or mask the signals Ligo is trying to detect. To combat this, advanced isolation techniques and sensors are employed to differentiate between the genuine cosmic signals and earthly noise, highlighting the constant dance between nature and technology. Here's something delightful. When Ligo detects a gravitational wave, it sends out alerts to observatories and scientists around the world. This global collaboration enables quick follow-up observations across different wavelengths of light, leading to a multi-layered understanding of cosmic events. It's like a cosmic symphony, where each instrument adds depth and richness to the overall piece. Speaking of symphonies, did you know that gravitational waves have frequencies that can be transformed into sound waves, allowing us to hear the universe? This process, called sonification, turns data into sound, offering a unique auditory experience of the cosmos. Imagine listening to the echo of a black hole collision, as if it's a melody played across the universe. And here's a whimsical thought. The precision needed to detect gravitational waves has led to advancements in other fields, such as timekeeping. The techniques developed for Ligo have been adapted to enhance the accuracy of atomic clocks, contributing to more precise time measurements. It's a reminder of how interconnected scientific progress can be, with innovations in one area sparking advances in another. Speaking of time, let's explore a captivating aspect of Ligo's discoveries. By observing gravitational waves, scientists are able to test general relativity in extreme conditions, verifying Einstein's theory with remarkable accuracy. Each detection serves as a miniature experiment, confirming the robustness of relativity and pushing the boundaries of our understanding of physics. Here's an exciting notion. LIGO's success has sparked the development of a new generation of space-based gravitational wave observatories. These future detectors, like the proposed LISA mission, will operate in space far from Earth's noise, allowing for even more sensitive observations of gravitational waves from the most distant and massive objects in the universe. Now, let's talk about the human aspect of this incredible journey. The LIGO project involves scientists, engineers, and students from all over the world, united by their passion for unlocking the mysteries of the universe. This diverse community collaborates tirelessly, sharing knowledge and expertise to push the frontiers of science. It's a testament to the power of teamwork and shared vision in achieving what once seemed impossible. Did you know that LIGO's groundbreaking work has inspired a new generation of astronomers and physicists? Educational programs and outreach efforts are encouraging young minds to pursue careers in science, ensuring that the torch of discovery continues to be passed down through the generations. It's a legacy of inspiration, lighting the way for future explorers of the cosmic unknown. Finally, consider the profound impact of LIGO's discoveries on our understanding of the universe. Each detection offers a glimpse into the violent and dynamic processes that shape the cosmos, painting a picture of a universe filled with cataclysmic events and intricate interactions. It's a reminder of the vastness and complexity of the world beyond our skies, inviting us to explore further and dream bigger. As we continue this journey, who knows what wonders await us in the ripples of space-time. Let me share a delightful insight. LIGO's ability to detect gravitational waves is not just a testament to human ingenuity, but also to patience and perseverance. The observatory was first proposed in the 1980s, but it took decades of development and refinement before the first gravitational wave was detected in 2015. This long journey highlights the dedication and vision of those involved, who kept their eyes on the stars despite the challenges. Now, here's something intriguing. The discovery of gravitational waves by LIGO confirmed the existence of binary black hole systems. Before LIGO's detections, these mysterious pairs of black holes were only theoretical possibilities. With gravitational waves, we've not only seen them, but also listened to their cosmic dance as they spiral and merge, providing a direct glimpse into some of the universe's most powerful interactions. Speaking of powerful interactions, did you know that the energy released during a black hole merger is so immense that it briefly outshines all the stars in the observable universe? It's as if the cosmos takes a moment to illuminate the hidden corners of its vastness, offering us a fleeting yet brilliant display of its incredible energy. Here's a curious fact. LIGO's detectors are so sensitive that they can pick up the faintest vibrations, including those caused by falling raindrops or distant ocean waves. This extraordinary sensitivity requires the observatories to be located in remote areas, far from human activity that could interfere with their measurements. It's a delicate balance, ensuring that the only whispers they hear are those from the universe itself. Speaking of whispers, the concept of gravitational waves was first predicted by Albert Einstein in 1916 as part of his theory of general relativity. However, it took nearly a century for the first direct evidence to be observed. This long gap between prediction and detection underscores the intricate dance between theory and experimentation that defines the scientific process. It's fascinating to consider that LIGO's discoveries have opened up a new field known as gravitational wave astronomy. This nascent field is still in its infancy, but it holds the promise of revealing secrets about the universe that were previously beyond our reach. Imagine being able to explore the cosmos through a new sense, one that allows us to feel the vibrations of distant worlds. Here's something you might find surprising. The gravitational waves detected by Ligo travel at the speed of light. This means that by the time they reach Earth, they carry with them messages from events that occurred millions or even billions of years ago. It's like receiving a postcard from a distant past, offering a glimpse into the universe as it once was. And did you know that Ligo's mirrors, crucial for reflecting laser beams to measure distance changes, are coated with a special reflective layer? This coating is designed to reduce thermal noise, ensuring that even the tiniest changes in distance can be detected. It's a marvel of engineering that combines precision with creativity, allowing us to peer into the cosmic ballet of gravitational waves. Speaking of creativity, the data analysis methods used by Ligo are inspired by techniques from other fields. For instance, algorithms initially developed for detecting music tones in a noisy environment are now employed to sift through Ligo's data for the unique chirps of gravitational waves. This interdisciplinary approach highlights how ideas from one area can illuminate another, driving innovation and discovery. Here's an enchanting thought. Ligo's success has inspired similar projects around the world, creating a vibrant network of gravitational wave observatories. This global collaboration ensures that gravitational wave detections are verified and studied from multiple perspectives, enriching our understanding of the universe. It's like assembling a cosmic puzzle, with each piece revealing a new layer of insight. It's also worth noting that the detection of gravitational waves has profound implications for our understanding of the universe's expansion. By studying these waves, scientists can gain insights into the rate at which the universe is expanding, a critical factor in unraveling the mysteries of dark energy. Consider this. The precision of Ligo's measurements has led to unexpected breakthroughs in other areas of science and technology, such as improving quantum computing techniques. The delicate balance required to detect gravitational waves has parallels in the world of quantum mechanics, sparking new ideas and innovations. And finally, imagine the dreams of future explorers inspired by Ligo's achievements. The thought that entire new generations will grow up in a world where listening to the universe is possible paints a picture of endless possibilities. The ripples detected by Ligo are more than just scientific discoveries. They are invitations to dream, explore, and transcend what we think we know about the universe. As you let these thoughts drift into your mind, consider the wonders that await us as we continue to listen to the whispers of the cosmos. Let me share with you a rather unexpected detail about Ligo's observatories. They rely on a pair of massive L-shaped vacuum tunnels, each running 4 kilometers in length. These tunnels are meticulously designed to house laser beams that bounce back and forth, measuring minute changes in distance caused by passing gravitational waves. Imagine the precision required to detect fluctuations as small as 1,000th of the width of a proton. It's almost beyond comprehension, yet it's exactly what Ligo's instruments are capable of achieving. Here's an intriguing thought. The very first detection of gravitational waves was almost an accident. The event, now famously known as GW15, occurred during a test run of Ligo's advanced detectors before the official start of its observation phase. This fortuitous timing meant that the equipment was finely tuned, allowing the team to capture this groundbreaking event. It's a testament to the importance of readiness and serendipity in scientific discovery. Consider for a moment the role of lasers in Ligo's operations. The observatory uses some of the most stable and powerful lasers ever created. They must maintain an unwavering beam over several kilometers without deviating, ensuring measurements remain consistent. This feat of stability requires an elaborate system of mirrors and vibration isolation to guard against even the slightest disturbances. The result is a laser system so fine-tuned that it can be likened to an instrument playing a celestial symphony. Isn't it fascinating that Ligo's sensitivity extends to detecting earthquakes and other natural phenomena? The observatories are equipped with seismometers that pick up the Earth's tremors. This capability not only helps in filtering out noise from gravitational wave signals, but also contributes valuable data to the study of geophysics. It's a beautiful example of how interconnected our scientific pursuits can be, where understanding one domain enriches another. Speaking of connections, did you know that the collaboration behind Ligo involves a global network of scientists? Over 1,000 researchers from more than 20 countries contribute to its success. This international cooperation ensures a diverse array of techniques and perspectives, enhancing the robustness and depth of findings. It's like a global brain, each neuron firing in unison to unlock the universe's secrets. Here's a captivating detail. The mirrors used in Ligo are not only coated to reduce noise, but are also polished to a level of smoothness almost beyond our imagination. Any imperfection on the mirror's surface could interfere with the laser's path, so they are crafted to be smooth to within a few nanometers. It's an art form in itself, where craftsmanship meets cutting-edge science to achieve the extraordinary. Have you ever wondered how Ligo manages to operate continuously, day and night? The observatories are staffed around the clock by dedicated teams who monitor the equipment and ensure everything runs smoothly. This persistent vigilance allows Ligo to capture gravitational wave events as they happen, no matter the time of day. It's a labor of love and commitment, ensuring we never miss a cosmic whisper. Here's another surprising aspect. The gravitational waves Ligo detects are not just a relic of the past, but also a blueprint for the future. By analyzing these waves, scientists can predict what might happen when similar cosmic events occur. This ability to foresee the cosmic ballet gives us a glimpse into future interactions, allowing us to anticipate and prepare for gravitational wave detections yet to come. Did you know that Ligo's achievements have inspired a wave of educational programs aimed at engaging the next generation of scientists? From interactive workshops to virtual reality experiences, these initiatives seek to fire up young minds about the wonders of the universe and the thrill of discovery. It's a powerful reminder of how science not only answers questions, but also ignites curiosity and imagination. Here's a thought-provoking notion. Some of the data collected by Ligo come from events that may never be directly observed through traditional telescopes. Gravitational waves can penetrate regions of space filled with dust and gas that obscure visible light. This capability to see invisible events opens up a realm of possibilities for understanding cosmic phenomena hidden from view, broadening our cosmic horizons. Imagine the meticulous planning that goes into coordinating observations with other telescopes around the world. When Ligo detects a gravitational wave, alerts are sent to a network of observatories, allowing them to point their instruments toward the source. This rapid response system maximizes the scientific yield from each event, creating a symphony of observation where every instrument plays its part in harmony. Here's a delightful tidbit. The term chirp, used to describe the sound of gravitational waves, comes from the resemblance to a bird's song as the frequency increases rapidly. It's a poetic reflection of how science often borrows from nature to communicate its most profound discoveries. This simple yet evocative term captures the essence of the cosmic interplay Ligo brings to our senses. Lastly, consider the technological advances that Ligo's demands have inspired. From quantum optics to advanced computing algorithms, the quest to understand gravitational waves has driven innovation across multiple fields. These breakthroughs not only propel our exploration of the cosmos, but also find applications in everyday technologies, showcasing the far-reaching impact of curiosity-driven research. As you drift further into this tapestry of discovery, let these stories of Ligo's wonders paint vivid dreams of the universe and the endless possibilities that await us in its embrace. Let me take you deeper into the marvels of Ligo and its quest to detect ripples from the fabric of the cosmos. Have you ever considered the sheer scale of these gravitational waves? They stretch and squeeze the space between the mirrors at Ligo by less than 1/10,000th the diameter of a proton. It's mind-boggling to think that such minuscule changes can be detected with such precision, isn't it? This sensitivity is a testament to human ingenuity and the relentless pursuit of knowledge. Speaking of precision, did you know that the lasers used in Ligo are so stable that their frequency varies by less than 1 part in a trillion? Imagine the challenge of maintaining such consistency over the long paths the lasers travel within the observatories. To achieve this, the lasers are meticulously tuned and stabilized, ensuring that even the tiniest variations are accounted for. It's like balancing on a cosmic tightrope, where every detail matters. Here's an intriguing aspect. The vacuum tubes that house these laser beams are among the largest in the world, stretching over 4 kilometers in length at each Ligo facility. Creating such a vacuum is no small feat. It requires maintaining pressures lower than those found in outer space, effectively isolating the lasers from air molecules that could interfere with their path. It's a quiet, invisible world inside those tubes, where the absence of air allows the whispers of the universe to be heard clearly. Have you ever wondered about the impact of Ligo's discoveries on our understanding of the cosmos? For instance, the detection of colliding black holes has provided new insights into how these enigmatic objects form and merge. Before Ligo, the existence of such collisions was largely theoretical. Now, with each detection, we're piecing together the life stories of black holes, revealing their mysterious dance through space and time. Let me share something fascinating about the team behind Ligo. It includes not only physicists and engineers, but also artists and educators who help translate complex scientific concepts into engaging and accessible forms. This multidisciplinary approach enriches the entire project, allowing for innovative ways to communicate the wonders of gravitational waves to the world. It's a beautiful blend of science and art, creating a bridge for understanding. Speaking of bridges, did you know that Ligo's discoveries have sparked new collaborations with other observatories, such as Virgo in Italy and Kagra in Japan? These partnerships form a global network that enhances the sensitivity and accuracy of gravitational wave detection. By working together, these observatories can pinpoint the location of cosmic events more precisely, like a trio of ears listening for the faintest echoes across the universe. Here's a surprising fact. Gravitational waves travel at the speed of light, yet they convey information about events that occurred billions of years ago. It's like receiving a postcard from the ancient universe, carrying messages from when galaxies were just forming. This time-traveling nature of gravitational waves allows us to look back into the history of the cosmos, unveiling stories that have been waiting eons to be told. Have you ever imagined the role of artificial intelligence in Ligo's operations? Complex algorithms are employed to sift through the vast amounts of data collected, identifying potential gravitational wave signals amidst noise. These intelligent systems can learn from past detections, becoming more adept at recognizing patterns that indicate cosmic events. It's as if Ligo has a digital assistant, tirelessly combing through the depths of space for clues. And consider this: each gravitational wave event detected by Ligo is given a unique name, much like a fingerprint, reflecting its discovery date. This practice adds a personal touch to these cosmic phenomena, transforming abstract data into memorable stories. These names serve as markers of our growing understanding, each one a chapter in the unfolding narrative of the universe. Speaking of narratives, did you know that Ligo's findings have challenged long-held assumptions about the universe? For example, the discovery of black holes with masses much larger than previously thought possible has prompted a re-evaluation of stellar evolution theories. It's a reminder of how science is a living, breathing endeavor, constantly evolving with each new revelation. Here's a delightful detail. Ligo's work has not only expanded our vision of the universe, but also inspired musicians and composers. The sounds of gravitational waves have been transformed into musical pieces, creating a unique fusion of science and art. These compositions allow us to experience the cosmos in a truly novel way, where sound becomes a bridge to the stars. Imagine the dedication required to operate Ligo. It involves constant maintenance and calibration of its highly sensitive equipment. The slightest misalignment or drift can affect the accuracy of detections, necessitating a vigilant eye and steady hand. It's akin to tending a delicate garden, where care and attention yield the sweetest fruits of discovery. Speaking of sweet fruits, consider the interdisciplinary benefits of Ligo's research. The technologies developed for gravitational wave detection are finding applications in diverse fields, from medical imaging to enhancing the precision of GPS systems. It's a fascinating demonstration of how curiosity-driven research can have far-reaching impacts, enriching our daily lives in unexpected ways. As we delve further into the mysteries of the cosmos, let these facts about Ligo inspire a deep appreciation for the interconnectedness of all things. Through the lens of gravitational waves, we're not just observing the universe, we're participating in its grand narrative, a story written in the language of ripples and echoes across the vast expanse. Let me take you on a journey into the heart of Ligo's extraordinary capabilities. Did you know that Ligo's precision is such that it can detect changes in distance smaller than a proton's diameter? Imagine trying to measure something so minute amidst the vastness of the universe. It's like being able to sense the gentle flutter of a butterfly's wings on the moon, a testament to the extraordinary sensitivity of this scientific marvel. Speaking of sensitivity, here's something that might surprise you. Ligo's detectors are so finely tuned that they must account for the Earth's natural vibrations, like those caused by ocean waves hitting the shore. These tiny tremors are part of the background noise that the system continuously filters out. It's an intricate dance of isolation where even the Earth's whispers must be quieted to hear the cosmic symphony. Did you ever think about how crucial timing is in gravitational wave detection? The timing must be synchronized down to a fraction of a second between Ligo's multiple observatories. This precision allows scientists to triangulate the source of the waves, creating a cosmic map that leads us back to the event that caused them. It's a bit like using the stars to navigate the vast seas of space-time. And here's a curious detail about the role of temperature. Ligo's instruments are sensitive enough that thermal fluctuations can impact their readings. The team goes to great lengths to control the environment around the detectors, maintaining a stable temperature to protect the delicate balance required for such meticulous measurements. It's akin to ensuring a perfectly tempered room for a delicate musical instrument to play its notes flawlessly. Imagine the challenge of distinguishing between a true gravitational wave signal and a false alarm. To achieve this, Ligo incorporates a fascinating method called blind injections, where fake signals are occasionally introduced to test the system's response. These surprise tests keep the team sharp, much like a fire drill ensures readiness for the unexpected. On the subject of unexpected challenges, have you considered the impact of local wildlife on Ligo's operations? In some instances, small animals like birds or insects can cause vibrations that must be accounted for. The team has developed ingenious methods to mitigate these disturbances, ensuring that the gentle hum of nature doesn't drown out the cosmic whispers they're trying to capture. Here's a thought-provoking aspect. The vast amount of data collected by Ligo is publicly available, allowing scientists and enthusiasts worldwide to engage with the findings. This openness fosters a community of collaboration and innovation, inviting fresh perspectives and unique interpretations of the cosmic messages we receive. And speaking of collaboration, did you know that Ligo's advancements have led to partnerships with space-based observatories? These collaborations aim to detect gravitational waves from different vantage points, enriching the tapestry of our cosmic understanding. It's like having a bird's-eye view alongside ground-level insights, offering a fuller picture of the universe's grand design. Consider the notion of time dilation, a fascinating consequence of Einstein's theory of general relativity. Ligo's ability to detect gravitational waves provides real-world observations of these effects, offering evidence of how massive objects like black holes can warp time and space. It's as if Ligo allows us to glimpse the universe's time-bending magic, a dance of physics unfolding before our eyes. Here's something that might intrigue you. The gravitational waves detected by Ligo often come from cataclysmic events like neutron star collisions. These events are not only sources of gravitational waves, but also creators of heavy elements like gold and platinum. It's a remarkable thought that the jewelry we wear might have origins in cosmic cataclysms, forged in the fiery hearts of stars eons ago. And let's not forget the educational impact of Ligo's discoveries. The project has inspired countless outreach programs, bringing the wonders of gravitational waves to classrooms and communities worldwide. It's a movement that sparks curiosity and ignites imaginations, encouraging a new generation to look up at the stars and wonder about the universe's secrets. A delightful tidbit to ponder. Ligo's success has led to discussions about building even larger and more sensitive gravitational wave observatories. These proposed projects, such as the Einstein telescope, aim to explore even fainter signals, pushing the boundaries of our cosmic hearing. It's a vision of the future, where each advancement propels us deeper into the mysteries of space. On the subject of future possibilities, have you imagined what detecting gravitational waves might mean for our understanding of dark matter? While still theoretical, the idea is that these waves could eventually provide clues about the elusive substance that makes up much of our universe. It's a tantalizing prospect that keeps scientists exploring, searching for answers hidden in the silent language of the cosmos. Finally, consider the enduring legacy that Ligo is building. With each detection, we add another piece to the cosmic puzzle, deepening our understanding of the universe and our place within it. It's a journey of discovery that invites us all to be part of something larger, a shared quest to unravel the mysteries that lie beyond our sight. As we continue to explore, Let these stories of Ligo remind you of the wonder and possibilities that await in the boundless expanse of the universe. Imagine for a moment the incredible precision required to measure gravitational waves. Ligo's technology is so advanced that it can detect changes in distance smaller than 1/10,000th the width of a proton. This level of sensitivity is akin to measuring the distance to the nearest star outside our solar system with a precision equal to the width of a human hair. Speaking of incredible feats, did you know that Ligo's detectors are housed in giant vacuum chambers, some of the largest ever built? These chambers remove air and other particles that could interfere with the measurements, creating an environment as close to space as possible on Earth. It's a testament to the lengths scientists will go to capture these faint echoes of the universe. Here's an intriguing aspect. The lasers used in Ligo must be extremely stable and powerful. They operate at 100 watts, which might not seem much, but these are among the most stable lasers ever developed. Any fluctuation in the laser light could mask the delicate signals of gravitational waves. Another fascinating detail is the role of computer algorithms in Ligo's operations. The vast amount of data collected requires sophisticated software to analyze it in real time. These algorithms sift through the noise to identify potential gravitational wave signals, acting like digital archaeologists uncovering hidden treasures. Speaking of treasures, consider this. The detection of gravitational waves has already resulted in Nobel Prizes. The 2017 Nobel Prize in Physics was awarded to 3 key scientists for their decisive contributions to the Ligo detector and the observation of gravitational waves. This recognition highlights the groundbreaking nature of Ligo's achievements. On the topic of groundbreaking discoveries, did you know that Ligo's success has sparked interest in building even more sensitive detectors? One proposal is the Cosmic Explorer, which would be 10 times more sensitive than current detectors. Such advancements could allow us to hear the faintest whispers of the universe, expanding our cosmic awareness. Here's something that might surprise you. Ligo has a sibling project in Italy called Virgo. Together they form a network that improves the ability to pinpoint the source of gravitational waves, much like how having multiple ears helps you determine the direction of a sound. This collaboration underscores the global nature of the quest to understand our universe. And speaking of global efforts, Ligo's international partnerships extend to India, where a new observatory is being built. This addition will further enhance the ability to locate gravitational wave sources, offering a more complete map of the cosmic events happening around us. Another remarkable aspect is how Ligo has redefined our understanding of black holes. Before its first detection of gravitational waves, black holes were mostly theoretical, with indirect evidence supporting their existence. Ligo's observations have provided direct evidence, confirming that these mysterious entities are not just figments of theoretical physics. Can you picture the challenge of maintaining Ligo's vacuum chambers? Even the tiniest leak could introduce noise that masks gravitational wave signals. To prevent this, the team regularly inspects and maintains the chambers, ensuring that they remain pristine environments for observing the universe's ripples. And here's a thought-provoking detail. The technology developed for Ligo has applications beyond astrophysics. Innovations in laser stabilization, vacuum systems, and data analysis have found uses in fields like medicine and quantum computing, illustrating the broader impact of this cosmic exploration. Let me share something intriguing. Ligo is capable of detecting gravitational waves from events that occurred billions of light years away. This means we are essentially listening to echoes from a time when the universe was much younger, offering a glimpse into its ancient past. Speaking of echoes from the past, consider the potential of detecting signals from the early universe itself. While this remains a goal for the future, such discoveries could provide insights into the conditions shortly after the Big Bang, helping us understand the fundamental nature of the cosmos. Here's something you might not expect. Gravitational waves could one day help us answer the question of how fast the universe is expanding. By comparing gravitational wave observations with electromagnetic signals, scientists hope to refine estimates of the Hubble constant, a crucial measure of cosmic expansion. Finally, reflect on the idea that LIGO is not just a scientific instrument, but a symbol of human curiosity and cooperation. It represents our collective desire to understand the universe and our place in it, a quest driven by wonder and the endless possibilities that lie in the cosmic unknown. As you drift into sleep, let your mind wander through the stars, inspired by the whispering tales of LIGO and the ripples it captures in the vast ocean of space-time. Let me tell you something quite surprising about LIGO. The detectors are long, straight arms stretching out to 4 kilometers each. These arms must be so perfectly aligned that even the curvature of the Earth had to be taken into account when they were built. That's right, the Earth's roundness is a factor in designing these straight pathways for the lasers. Have you ever wondered about the mirrors at the heart of LIGO's detectors? They are not ordinary mirrors, but rather highly polished, super-reflective mirrors made of fused silica. Each one weighs about 40 kilograms and is suspended by thin glass fibers to isolate them from any vibrations. This delicate suspension system is crucial because even the slightest movement could disrupt the detection of gravitational waves. Speaking of delicate systems, did you know that LIGO's detectors can sense changes as small as 1/100th of a billionth of the diameter of an atom? It's like detecting a change in the length of Los Angeles to New York by less than the width of a human hair. This dazzling precision is achieved through a technique known as laser interferometry, where laser beams are split and then recombined to detect minute changes in length. Here's a fascinating tidbit. The lasers used in LIGO are some of the most stable in the world. Developed specifically for this purpose, they need to maintain a steady beam to prevent any noise that could interfere with the detection. These lasers are so precise that they redefine what's possible in terms of light stability, setting new benchmarks for future technologies. And speaking of groundbreaking technologies, did you know that the data LIGO collects is shared almost immediately with astronomers around the globe? This collaboration allows for rapid follow-up observations, helping to pinpoint the gravitational wave source and gather more information about cosmic events. It's a beautiful example of the international scientific community working together, united by a shared curiosity about the universe. On the topic of international collaboration, the gravitational wave network is expanding beyond LIGO and Virgo with the addition of Kagra in Japan. This observatory is unique because it is built underground, helping to insulate it from surface noise. This innovative approach further increases the precision of gravitational wave detection and contributes to a more comprehensive understanding of the universe. Here's an intriguing thought. LIGO's success has inspired scientists to think beyond Earth. There are plans for space-based gravitational wave detectors, like the proposed LISA mission by the European Space Agency, with spacecraft forming an equilateral triangle millions of kilometers apart. These detectors could open an entirely new window to the universe, capturing waves from massive black holes merging in distant galaxies. Can you imagine the potential of detecting ripples from unknown sources while we've observed waves from black hole and neutron star mergers? There's a possibility of discovering entirely new phenomena that produce gravitational waves. This prospect fuels the excitement and anticipation among scientists, as each detection could unveil secrets we never knew existed. Speaking of discoveries, did you know that Ligo can also detect gravitational waves from spinning neutron stars, known as pulsars? These stars are like cosmic lighthouses, emitting beams of radiation as they spin. If they are not perfectly spherical, they can emit gravitational waves, providing another avenue for exploration and understanding of these dense remnants. Here's a surprising application of Ligo's technology. Its ultra-stable lasers and precise measurement techniques have inspired advancements in Earth-based technologies such as earthquake detection and monitoring. By adapting Ligo's methodology, scientists can better understand and predict seismic events, potentially improving early warning systems. Reflecting on the broader implications, Ligo's findings challenge our understanding of extreme physics. For instance, the detection of black hole mergers has provided insights into their properties, such as their spins and masses, which were previously just theoretical predictions. Each observation helps refine our models of the universe, painting a clearer picture of the complex dance of celestial bodies. And here's an intriguing insight. Ligo has contributed to our understanding of the life cycle of stars. By observing neutron star mergers, it has helped confirm theories about how these events produce heavy elements like gold and platinum. This celestial alchemy enriches our knowledge of how the elements that make up our world are formed in the cosmos. Ligo's role in education is also noteworthy. It has inspired new generations of scientists and engineers, providing a tangible example of how curiosity and persistence can lead to groundbreaking discoveries. Through public outreach and educational programs, Ligo shares the wonder of gravitational wave astronomy with audiences of all ages, igniting imaginations and fostering a love for science. Let us also appreciate the artistry involved in constructing Ligo. The observatory is not only a feat of engineering, but a masterpiece of interdisciplinary collaboration, blending physics, mathematics, computer science, and engineering. This synthesis of talents and ideas is essential for tackling the immense challenges posed by gravitational wave detection. Finally, consider how Ligo represents a profound philosophical shift. It exemplifies humanity's ability to listen to the universe rather than just look at it. By detecting these faint ripples in space-time, we have added a new dimension to our exploration of the cosmos, enriching our understanding of the universe and our place within it. As you gently drift into a world of dreams, let your thoughts wander through these celestial mysteries, pondering the endless possibilities that lie ahead. Let me share something intriguing. Ligo's observatories are designed to operate in pairs, with one located in Livingston, Louisiana, and the other in Hanford, Washington. This dual setup allows them to cross-check each other's detections, reducing the likelihood of false alarms. Isn't it fascinating how these twin observatories work in harmony across the continent? This configuration also helps pinpoint the location of gravitational wave sources more accurately by timing the arrival of waves at both sites. Speaking of precision, did you know that Ligo's interferometers must be kept at an incredibly stable temperature to function correctly? The temperature is controlled to within a fraction of a degree, as even the slightest fluctuation could affect the laser beam's paths. Imagine the meticulous care required to maintain such conditions, ensuring that nothing disturbs the delicate balance necessary for detecting these cosmic whispers. And here's something curious. The arms of Ligo's interferometers are 4 kilometers long and housed in vacuum tubes to prevent air molecules from scattering the laser beams. This vacuum is so complete that it rivals the conditions of outer space. It's an extraordinary effort to create an environment as pristine as possible, allowing the lasers to travel unobstructed. Now, consider this. LIGO's detectors are so sensitive that they can be influenced by passing clouds, changes in the Earth's gravitational field, caused by variations in atmospheric pressure, can slightly stretch or squeeze the ground. This surprising sensitivity emphasizes the incredible challenges faced when isolating gravitational wave signals from everyday environmental noise. Here's an unexpected fact. LIGO's sensitivity enables it to detect gravitational waves from events that occurred billions of light years away, reaching us across vast cosmic distances. This capability allows scientists to study the universe's most cataclysmic events, offering a glimpse into places and times we could never hope to observe directly with traditional telescopes. Reflecting on technological advancements, did you know that LIGO's mirrors are coated with thin layers of reflective material, precisely engineered to enhance their reflectivity? These coatings consist of multiple layers of materials with different refractive indices, carefully tuned to maximize the amount of light reflected back down the arms of the interferometer. It's a marvelous example of how even the tiniest details are critical to the success of this ambitious project. Here's another captivating fact. LIGO's success in detecting gravitational waves has provided a new way to test Einstein's theory of general relativity. By observing the properties of these waves, scientists have found that they behave precisely as predicted by Einstein over a century ago, further cementing his groundbreaking theory as one of the pillars of modern physics. Isn't it remarkable how a theory from the early 20th century continues to shape our understanding of the universe today? And did you know that the detection of gravitational waves has opened a new field of astronomy known as multi-messenger astronomy? This approach combines information from gravitational waves, light, and other electromagnetic signals to provide a more comprehensive view of cosmic events. By integrating these diverse data sources, scientists can gain deeper insights into phenomena such as neutron star mergers and the formation of black holes. Here's something delightful. LIGO's discoveries have inspired a renewed interest in the cosmic origins of elements. Gravitational waves from neutron star mergers have confirmed that these collisions are a primary source of heavy elements like gold and platinum in the universe. This finding enriches our knowledge of cosmic chemistry, connecting the stars' life cycles to the material world around us. Consider this remarkable insight. The gravitational waves detected by LIGO travel at the speed of light, sweeping across the universe like gentle ripples on a cosmic pond. This swift journey allows them to convey information about their sources, carrying the signatures of the massive objects that created them. By analyzing these signals, scientists can reconstruct the events that shaped them, unlocking secrets of the universe's most powerful forces. Speaking of analysis, did you know that LIGO's data is so complex that it requires sophisticated algorithms and powerful computers to process? These algorithms sift through massive amounts of information to extract the faint gravitational wave signals from the background noise. This impressive computational effort is a testament to the advances in data science and machine learning, driving innovation across multiple fields. And here's an inspiring thought. LIGO's achievements highlight the power of human curiosity and the relentless pursuit of knowledge. By venturing into unknown territories and embracing technological challenges, scientists have expanded our understanding of the universe, pushing the boundaries of what we thought possible. Reflecting on LIGO's impact, consider how it has changed the way we perceive the universe. Before the detection of gravitational waves, our understanding of cosmic events was limited to what we could see. Now we can also listen to the universe, capturing the symphony of celestial phenomena and gaining a richer, more nuanced view of the cosmos. As you ponder these wonders of gravitational waves and Ligo's incredible journey, let your imagination drift through the vastness of space. Envision the possibilities that lie ahead as we continue to unravel the mysteries of the universe, one ripple at a time. Let's explore this together. Have you ever wondered how Ligo can isolate the faintest whispers of the cosmos amidst the cacophony of earthly noise? It's fascinating to know that Ligo is placed in remote locations to minimize human-made vibrations. These sites are carefully chosen to be far from urban centers, where the hustle and bustle could interfere with the delicate measurements. This geographical solitude is crucial for the sensitive instruments to pick up the subtle tremors of gravitational waves. Here's another interesting detail. The mirrors used in Ligo's interferometers are polished to an astonishing degree of smoothness. The surface irregularities on these mirrors are smaller than a fraction of a wavelength of light. This precision ensures that the laser light reflects without distortion, maintaining the integrity of the signals. The craftsmanship involved in creating these mirrors is truly an art form in itself. And speaking of craftsmanship, did you know that Ligo operates at a frequency range that is specifically tuned to detect the most common sources of gravitational waves? This range, between 10 and 2000 Hz, is perfect for capturing the waves produced by merging black holes and neutron stars. It's like tuning a radio to the right station, allowing scientists to hear the cosmic symphony that would otherwise be lost in the noise. Now, let me tell you about the collaborative nature of Ligo's operations. The data collected is shared with a global network of scientists and observatories. This collaboration extends across continents and allows researchers worldwide to contribute to the discovery process. It's a beautiful example of how science transcends borders, uniting us in the quest for knowledge. Here's something delightful. The calibration of Ligo's instruments involves injecting simulated signals into the system. These artificial signals help scientists test and refine their data analysis techniques. It's like rehearsing a play before opening night, ensuring that everything functions flawlessly when a real gravitational wave passes by. Did you know that Ligo's detectors are so sensitive that they can even sense the vibrations caused by ocean waves hitting distant coastlines? This surprising sensitivity is a testament to the engineering marvel that Ligo represents. The ability to detect such subtle changes in the environment underscores the challenge of distinguishing genuine gravitational wave signals from other sources of noise. And here's an unexpected twist. Ligo's discoveries have inspired new theories about the nature of black holes. Before the first detection of gravitational waves, black holes were largely theoretical constructs. Now, with direct evidence of their existence, scientists are revisiting and refining their understanding of these enigmatic objects, exploring questions about their formation and evolution. Consider this. The detection of gravitational waves has opened up new possibilities for studying the early universe. By examining the properties of these waves, scientists hope to learn more about the conditions that existed shortly after the Big Bang. It's as if we're gradually deciphering a cosmic code, revealing the secrets of the universe's infancy. Speaking of revelations, did you know that the detection of gravitational waves has confirmed the existence of binary black hole systems? These systems, where two black holes orbit each other, were previously suspected but never directly observed. Ligo's observations have provided concrete evidence, shedding light on the dynamics and frequency of such cosmic pairings. And reflecting on technological advancements, consider how LIGO's discoveries have driven innovations in other fields. The techniques developed for isolating and analyzing gravitational wave signals are influencing areas like signal processing, data analysis, and even quantum computing. It's a reminder of how breakthroughs in one domain can ripple across various disciplines, sparking new ideas and applications. Here's something intriguing. LIGO's continuous upgrades and enhancements mean that its sensitivity improves over time. With each iteration, the detectors become more adept at capturing faint signals, expanding the range of astronomical events they can observe. This ongoing evolution ensures that LIGO remains at the forefront of gravitational wave astronomy, poised to uncover new cosmic phenomena. Have you ever imagined the possibility of detecting gravitational waves from sources beyond our galaxy? LIGO's sensitivity enables it to detect signals from extragalactic events, offering a glimpse into the distant reaches of the universe. This capability allows scientists to study events that occurred millions or even billions of years ago, broadening our understanding of cosmic history. And lastly, ponder this. LIGO's success is a testament to the power of perseverance and collaboration. The project took decades to come to fruition, requiring the dedication and expertise of countless scientists, engineers, and researchers. Their collective efforts have brought us to the brink of new discoveries, demonstrating the incredible achievements that are possible when we work together towards a common goal. As you reflect on these surprising facts, let your mind wander through the endless possibilities that lie ahead. Envision the future discoveries that await us as we continue to listen to the universe's whispers, each ripple bringing us closer to understanding the profound mysteries of existence. Allow these thoughts to lull you into a restful state, knowing that the journey to unravel the cosmos is as infinite as the stars themselves. Let's explore another curious facet of LIGO. Did you know that the lasers used in LIGO's interferometers are some of the most stable and pure in the world? These lasers emit light that is nearly identical in wavelength, ensuring that the interference patterns detected are as clear and precise as possible. It's almost like having a perfect pitch in music, where even the slightest deviation could throw off the entire symphony. Speaking of precision, consider the extraordinary temperature control required for LIGO's operation. The equipment must be kept at an incredibly stable temperature to prevent thermal fluctuations from interfering with detection. The mirrors, for instance, are enclosed in vacuum chambers to minimize thermal noise. It's fascinating how even the slightest change in temperature could affect the whole process, akin to how a single pebble can ripple the surface of a calm pond. Now, here's something that might surprise you. The data collected by LIGO is so voluminous and complex that it requires the use of supercomputers for analysis. These computational powerhouses sift through the noise to find the faint signals indicating gravitational waves. Imagine searching for a whisper in a crowded room. That's the kind of challenge these computers tackle, tirelessly working to unlock the secrets of the universe. Reflecting on the human element, there's a dedicated team known as gravity spies who helps sift through data to distinguish real signals from noise. Volunteers from around the globe participate in this citizen science project. It's a beautiful example of how individuals, regardless of their background in science, can contribute to groundbreaking discoveries. This collective effort shows how the pursuit of knowledge is truly a universal endeavor. And did you know that LIGO's impact extends beyond physics? Its discoveries have sparked philosophical and existential questions, prompting us to reconsider our place in the cosmos. The ability to detect something as elusive as gravitational waves challenges us to expand our understanding of reality and our relationship with the universe. It's a gentle reminder of the vastness of what remains to be explored. Here's another intriguing thought. The concept of gravitational waves was first proposed by Albert Einstein over a century ago in his theory of general relativity. It's amazing to think that such a groundbreaking theory laid the groundwork for discoveries happening today. Einstein himself once doubted that these waves could be detected, and yet, here we are, proving that even the most ambitious ideas can someday become reality. Speaking of historical milestones, the first detection of gravitational waves in 2015 was a momentous event that marked the beginning of a new era in astronomy. It confirmed a century-old prediction and opened a new window through which we can observe the universe. This event was so significant that it earned the scientists involved the Nobel Prize in Physics, a testament to the monumental impact of their work. As we delve deeper, consider this. Gravitational waves travel through space at the speed of light, carrying information about their origins and the nature of gravity itself. This means that every time we detect a wave, we're essentially receiving a message from the distant past, a broadcast of cosmic events that unfolded billions of years ago. It's a humbling thought, knowing that each ripple is a relic of a bygone era. Imagine, too, the possibilities that arise from multi-messenger astronomy, a field that combines gravitational wave data with information from other sources like electromagnetic radiation and neutrinos. This integrated approach allows scientists to form a more complete picture of cosmic events, akin to hearing a melody that was once only a single note. The synergy of different observations provides insights that were previously beyond our grasp. Here's a delightful tidbit. The incredible sensitivity of LIGO's detectors means they are affected by the tiniest disturbances, even those caused by seismic activity. To counteract this, the observatory employs advanced seismic isolation techniques to shield the instruments from vibrations. It's like creating a calm oasis in the midst of a bustling city, allowing the instruments to focus solely on the whispers of the universe. In contemplating the vastness of space, it's worth noting that LIGO's discoveries have profound implications for our understanding of the universe's structure and evolution. By studying gravitational waves, scientists can probe the most extreme conditions, from the heart of colliding black holes to the echoes of the Big Bang itself. It's as if we're slowly piecing together the grand puzzle of the cosmos, one discovery at a time. Moreover, each detection serves as a reminder of the interconnectedness of our world. The ripples of gravitational waves span vast distances, touching everything in their path, including us. It's a subtle yet profound connection, illustrating how events light years away can have an impact right here on Earth. It's a testament to the intricate tapestry of existence that binds us all. As we draw closer to understanding the universe's mysteries, let your thoughts drift through the possibilities that lie beyond the horizon. Each new discovery is a promise of the wonders yet to be revealed, a gentle nudge to continue exploring, dreaming, and seeking answers to the questions that have captivated humanity for generations. Allow these contemplations to guide you into a state of serene reflection as the universe's whispers softly echo in the stillness of the night. Let's marvel together at the fact that the precision required for LIGO's measurements is akin to measuring the distance to the nearest star, Alpha Centauri, down to the thickness of a human hair. It's almost beyond comprehension, isn't it? This level of precision highlights the extraordinary capabilities of LIGO and the dedication of those who maintain and operate it. Here's a delightful thought. The mirrors used in Ligo's detectors are so finely polished that any imperfection is smaller than a fraction of the wavelength of light. Such an incredible level of detail ensures that the mirrors reflect light with minimal distortion, maintaining the accuracy of the measurements. Did you know that gravitational waves are produced by some of the most violent events in the universe, like the collision of black holes or neutron stars? These cataclysmic occurrences release energy far surpassing that of all the stars in the observable universe combined. Imagine the immense power harnessed in a single wave, traveling across the cosmos to tell its tale. Speaking of energy, here's a fascinating fact. When two black holes merge, the energy released in the form of gravitational waves can be greater than that of 1 billion suns. This unfathomable force is what Ligo is designed to detect. Let me share something intriguing about the L-shaped design of Ligo's detectors. Each arm is 4 kilometers long, stretching across the landscape like giant tuning forks. This configuration is essential for detecting the minute changes caused by passing gravitational waves. Can you picture such an impressive structure, quietly listening for the universe's faintest whispers? Moreover, these arms house vacuum chambers that are among the largest in the world, ensuring that the laser beams within are not disturbed by air molecules. This pristine environment is crucial for achieving the necessary sensitivity. Here's something to ponder. Ligo's instruments are so sensitive that they can detect vibrations from a passing truck miles away. To minimize such disturbances, the observatories are situated in remote locations surrounded by vast stretches of land that act as natural buffers. This strategic placement helps ensure that the only vibrations captured are those from the cosmos, not from earthly activities. In addition to their isolation, the instruments are suspended in a way that decouples them from ground vibrations, using a series of pendulums to absorb unwanted movements. It's fascinating to learn that Ligo's detectors use laser beams that bounce back and forth between the mirrors thousands of times. This process increases the effective length of the arms, enhancing the precision of the measurements. It's like creating an optical path far longer than the physical structure, amplifying the sensitivity to gravitational waves. The laser technology itself is an engineering marvel, producing beams that are both incredibly stable and intensely focused, capable of maintaining their integrity over the long distances involved. Consider the crucial role of the interferometer, the heart of Ligo's detection system. This instrument splits a laser beam into 2 paths, which later recombine. If a gravitational wave passes through, it alters the lengths of these paths ever so slightly, creating an interference pattern that signals the wave's presence. It's akin to a cosmic dance, where the steps are recorded in the subtle shifts of light. The precision of this dance is ensured by the purity of the light used, which is filtered to remove any fluctuations that could obscure the delicate signals. Did you know that Ligo is part of a global network of observatories, including Virgo in Europe and Kagra in Japan? This international collaboration enhances our ability to pinpoint the source of gravitational waves, much like using multiple microphones to locate the direction of a sound. The synchronization of these observatories allows for a more comprehensive understanding of the events that generate these waves. Together, they provide a more detailed picture of the universe and its dynamic processes. Here's another surprising aspect of Ligo's contribution to science. Its technology has spurred advancements in other fields, such as medicine and telecommunications. The innovations developed for gravitational wave detection have been adapted to improve medical imaging techniques and enhance data transmission capabilities. It's a wonderful reminder of how scientific exploration can have far-reaching benefits beyond its original intent. This cross-pollination of ideas exemplifies the interconnected nature of scientific discovery and its potential to enrich our lives. Imagine the excitement when LIGO detects a gravitational wave signal, triggering alerts to observatories around the world. This rapid response allows astronomers to focus their telescopes on the source, capturing complementary data in real time. It's a coordinated effort that combines the strengths of multiple disciplines, providing a richer narrative of cosmic events. This synergy extends our observational reach, offering insights that were once the domain of imagination. Let's explore the concept of polarization in gravitational waves, a feature that LIGO can measure. Polarization refers to the orientation of the wave's oscillations, offering clues about the source's properties and the environment it traverses. By analyzing these patterns, scientists gain insight into the fundamental nature of gravity and the fabric of space-time itself. This deepens our comprehension of the universe, revealing layers of complexity within the seemingly simple ripples. Lastly, consider the profound impact of LIGO's discoveries on our understanding of black holes. Prior to the detection of gravitational waves, black holes were largely theoretical constructs. Now, with each wave, we gather concrete evidence of their existence and behavior. This tangible proof transforms enigmatic concepts into observable phenomena, bridging the gap between theory and reality. It signifies a new era in astrophysics, where the hidden can be unveiled with patience and ingenuity. As we conclude this gentle exploration of LIGO and its wondrous capabilities, let these thoughts carry you into a peaceful slumber. The universe, with all its mysteries, continues to inspire wonder and curiosity. May your dreams be filled with the endless possibilities that lie within the cosmic tapestry, waiting to be discovered by the dreamers and explorers of tomorrow.